Hi, in this video, we want to take a look at linear correlation using Python. So once again, we're using Introduction to Statistics with Python as a textbook. And first thing we're going to do, we're going to take a look at computing a regression line. So this will be simple linear regression. So in this situation, we're looking at the case where we have y is equal to mx plus b plus some kind of randomness in there. So what we're really looking at, how we're thinking about this is that in our minds, we don't really think about the random aspect because the random aspect is something we can't really control. So we're looking at this as the expected value of y is equal to m times x plus b. So we've got a straight line equation, just like we did in middle school or high school or college algebra, where you're using this. All right, so this is, mathematically really the simplest model that I could possibly get to relate x and y. So what we're in a situation where x is some value that we know, and what we want to do, we want to predict the value of y. Or for a particular value of x, we want to know what is the average value of y. These are the two situations that we were interested in. So there's prediction and there's inference on the average. And they look very similar and they feel very similar, but from a mathematics and statistics point of view, they're two very different questions. But for us, we're saying that there is a straight line relationship between x and y as our variables. Then after that, we're going to take a look at correlation. All right, so as always, first thing I want to do, I want to load my packages. So let's go ahead and get matplotlib, numpy, matplotlib pyplot, scipy stats, pandas, numpy linear algebra. Specifically, we're going to get the least squares function from there. We're going to get the code that we need to use URL open to get the data, and then with stats models API as SM. Okay, so now that we've got our tools loaded into Python, let's go ahead and start doing some regression. So when I talk about regression, what I'm saying is that the variable y has a functional relationship on x, and on average, that relationship is mx plus b, a straight line. All right, so what we want to do, we want to fit a line. Now, there are tons and tons and tons of ways to fit a line. The gold standard for doing this is what's called ordinary least squares method of fitting. So what we're going to do, we want a straight line that gives me a predicted y value. I'm going to take the observed y value. I'm going to take the predicted y value. I'm going to subtract the two. Then I square it. Okay, so that gives me the squares aspect of ordinary least squares. Take the y value, the predicted y value, subtract, square it. Now, I'm going to do that for every single value of y. And then after I square each of them, I'm going to add them up. And what I want to do, I want my modeled value of y set up so that that sum of all those squares is as small as possible. So remember, if I square something, it's either 0 or a positive number. So I'm adding up a bunch of, for the most part, positive numbers. There may be a few zeros in there, but don't worry about that. All right, so my idea is I want to make this as that sum of squares as small as possible. And so we're going for ordinary least squares because we want the least sum of squares possible. All right, so let's go ahead and look at an example. Let's take some data for 24 type 1 diabetic patients. And we're going to look at their fasting blood glucose and look at their mean circumferential shortening velocity. And that's coming from echocardiogram. So what we want to do, we want to relate the blood glucose when they're fasting to the circumference shortening velocity. All right, so now let's go ahead and get the data. So it's all about that base, no trouble. I'm going to take the URL base right here. So here's the base URL for me. This mamma jamma line, this character string. So this is a character string all written out. It's all beautiful. And I'm going to take this part specifies which file, which part of the web page to go to. And then we're going to use the plus symbol to concatenate the two. We're going to take the URL base and end file, and we're going to paste them together like that. We're going to concatenate, and then we're going to use that as our URL. So now let's go ahead and take a look. So you can see I've got the whole thing written out in this manner. So the Altman 11.6.txt was the in file portion that we got over here. Now what we're going to do, we're going to use URL open and the URL that we just created over here, and we're going to grab the data. Then what we're going to do, we're going to pass that to generate from text function. We're going to say, hey, this is comma delimited data set. Take this comma delimited data set and convert it to some data for us. All right, so boom, let's do that. All right, so now let's take a look. Let's see, what do we get in the end? All right, so I can see that I've got 2 columns of data in an array. All right. Now, hey, there's an NaN in here. All right, not a number. This is a missing value. Okay, missing values are a big deal in data. These are always going to come up. Okay, we have several choices whenever we deal with missing data. We can either, one, throw it out, or replace it, or impute a value. So impute means I take that position and I enter some number that is very reasonable for that spot. All right, for us, for this problem, we're going to omit. If you're doing standard linear regression, the default is to omit. If you don't do something proactive, it's going to throw out the observations. So you always need to be mindful about this. In general, the gold standard is to omit it. But I can tell you, if you're doing machine learning, most of the time, imputing is a better way to go. If you're doing something with artificial intelligence, machine learning, data mining, usually we want to put a fake value, or maybe not fake, surrogate value in there. But in classical statistics, the standard is to just throw out the entire observation. There's some problems with that. There's problems in any direction you can go. All right, so what we want to do now, we want to go ahead and we want to like compute this by hand. We want to kind of manually go through this so that we have more of an intuition on what's going on when we do this later. Now, I'm going to do this kind of the clunky dumb way first. That's the by hand method, because I want us to kind of take a look, see what's going on. And then we're going to do it the smart way by letting Python do the work for us. All right, so here, NP where, and I have NP is in a data. All right, so what's going on is that we're going to take a look at where do we have that missing value, and we want to get rid of it. Okay, so A and B, F9, and you notice that I'm saving it in A and B, so A, B. All right, so we can see that in the first position, the row is 15, the column is 1. Now remember, Python indexes starts with 0. So really, this is the 16th row. This is the second column. Okay, so we know if I was to count down the list in my data, this position is the 16th row and the second column, even though Python reports 15 and 1. All right, now what I'm going to do, I'm going to take that row and I'm going to throw it out. I'm going to throw out the entire row of that has the missing value. In standard regression, if you're missing one value off an observation, you throw out the whole thing. This may be a good way to go. This may be a bad way to go. Later down the road, when you get into more advanced machine learning techniques, you need to be mindful about this. All right, so now I went through and I deleted that one position. And so I can see that I don't have any missing values left. So I have one fewer observation than I had a moment ago. All right, so now let's go ahead and let's just set it up so it's a little bit easier to work with. So I'm taking the first column is X, the second column is Y. That's what this code does. And we're just kind of taking a look, seeing what we get. Kind of interesting. Now let's go ahead and plot it. All right, so I can see that I've got a scatter plot, and there's kind of a trend going up from upwards as we move left to right. So here I'm kind of looking at like probably a positive slope. You know, this goes here, it goes from 4 to 20, and here it goes from 1 to, you know, about 20 also, something like that ish. Where's that? Well, it's 1.0. Okay, so from 1 to 2. All right. Well, you know, so it's not a very crisp line. I can see it's very scattered. So looking at this, honestly, I would not trust this for a linear regression model unless I had other prior knowledge and understanding that's going on. But we're going to run with the example because it's what we've got to work with. All right, so now we want to take a look at what's called a design matrix. A design matrix is just basically the setup of our predictor variables. But there's a twist to it. So let's look at this. So our standard notation is that we use the letter X to represent our predictor variables and the letter Y to represent our response variables. Y is for our target variables and X is for our predictor variables. And that's why, and this is the X matrix. That's why I call it X mat. All right, so here are all of the X values over here on the right. And if I just look through, those are the values that we were seeing earlier. Look through, if I go like this, if I type in X, I can see that's like 15.3, 10.8, 8.1. I look up here. Yep. I got those values going through here. Now, what's going on with this column of ones? All right, remember, my equation is going to be y equals mx plus b. All right, so m is the slope, b is the y-intercept. Now, if I think about it, that m is getting multiplied by x, correct? So when I do the math, this column with the varying numbers, this corresponds to, like when I work this out, this column is going to correspond to that m, that slope. Over here, if I think about y equals mx plus b, the y-intercept is a constant value. It's constant. What do I have going down this column? I have constant values. They're all ones. Okay. And in regression, if you're going to compute this, we always put it in ones instead of some other constant value. And this is the standard way to approach this in statistics. So the ones correspond to the y-intercept, and the predictor variable column corresponds to the slope after I'm done doing all my calculations. All right, so now let's go ahead and actually calculate the parameters and see what we get. All right, so I'm using the least squares function. I'm putting in my predictor matrix. So the column with all ones and then the column of x's. I've got my y values, and our cond, we don't really need to worry about that for now. All right, so now let's take a look. All right, so the ones that we want to look at right now, things that are most important to us, are these two values. These other two are important, but we'll get into those in a future lecture. All right, so here, this is going to be my y-intercept, and this is going to be my slope. So remember, when I looked at that x-mat matrix, the first column was the constant. That was my y-intercept. Here is my y-intercept. There is the first one. First column is constant, y-intercept. The first thing that I see here is the y-intercept. Now, remember, the slope corresponds to the second column. So the second value, this is my slope. So I'm looking at it and seeing that the slope of the line is going to be 0.02 approximately. All right. And does that seem reasonable? Considering that this goes from like 1 to 2 And this goes from 4 to 20. Yeah, looks reasonable. And we can print it out another way. Here's just a little bit cleaner. All right, now that was the dumb way. That's the way that we wouldn't want to do it. We would want to just kind of let Python do all the heavy lifting for us. And you'll notice that Pandas handles that missing value automatically for us. And when I do it this way, I don't have to worry about the missing value. I just drop it in, and Python knows to kick that row out, that row of data out. All right, so let's go ahead and pull in something from stat models formula. And let's go ahead and get our data frame. And since I'm using a data frame, it looks so much better. And here I've got glucose, I've got my X values, and I've got the circumference, velocity in there. Now I want to actually go through and fit the model. So what we're going to do, we're going to take stats models formulas, and then I'm going to do ordinary least squares. Ordinary least squares, remember, what I'm trying to do, I'm trying to minimize the, I'm going to take the difference from the observed and the model value. I'm going to square it, and then I'm going to add up all those squares. And I want that total added value for all the squares, the total addition, to be as small as possible. And that's what I mean by ordinary least squares. Here, I'm using the formula notation again. Notice I've got the tilde. So here, we're saying that the VCF column statistically depends on glucose. That's what this tilde notation means. Here, we're passing the DF data frame, and we're trying to get the fitted model. All right, so now let's take a look. All right, so if I look here, I can see that the intercept is 1.1 about, which matches what we got previously. And the slope is going to be 0.02, which is what we got here. So it's looking pretty good. All right, so that is a simple linear regression model. That's how we can compute it 2 different ways. So now let's start talking about correlation. All right, there are 3 major types of correlations. Now there are tons and tons of different ways to measure correlation, but the 3 big ones are Pearson, Spearman, and Kendall. Okay, Pearson correlation. This is, I'm skipping ahead. I'll go ahead and skip down. All right, so Pearson correlation, that is straight line correlation. This computes the correlation under the assumption that there's a straight line relationship. If it's not a straight line correlation, like there's some curvature or something else going on, this will not perform very well. Or it won't perform as well as it could, I should say. So this is by far the default, most well understood version of correlation. When most people say correlation, either they're not talking mathematically at all, or they mean this kind of correlation. It's one of the two, and you have to kind of judge what the person's saying. This is almost always the correlation that people use. This is the fastest one to compute also. This has, from a statistics point of view, this has a lot of good properties. It's very intuitive. You can work things out by hand relatively easy. It's a pretty good way to go. But it is straight line correlation. So if you are working in the situation where you're not modeling necessarily a straight line, like there could be some curvature, then this is usually not the best one to use. The next one to think about is Spearman correlation. This is also called rank correlation. What this does, this converts the data to its rank and then does the Pearson correlation on that. All right, so what do I mean by the rank? Take the least value, replace that with a 1. Take the second least value, replace it with a 2. Take the third least value, replace it with a 3. Take the fourth least value and replace it with a 4. Take the fifth least value and replace it with a 5. And you keep on doing this until you get all the numbers from 1 to n, where n is your sample size. You do that for all the variables you're doing the correlation with, and then you run the Pearson correlation on the numbers 1, 2, 3, 4 of the rank. Okay, why do we do this? This does a better job of detecting non-straight line relationships between data. And this is the one that I personally prefer. This is the one I usually use because most of the time I'm not restricted to straight line statistical models. If I'm restricted to a straight line statistical model, I'm going to be using Pearson. The next one to talk about is called Kendall's tau, and this is concordance. So what we do is we go through and we take every pair of observation we can get. So we take like row 1 and row 2. One of those two have a lesser x value. If the one with the lesser x value has the lesser y value also, that's a +1. If the lesser x value has the greater y value, that is a -1. And then we look at the first observation with the third observation. If the lesser x value also has the lesser y value, that's a +1. If the lesser x value has the greater y value, that is a -1. And it goes through and computes all this. Now, if you're not tracking, you don't understand what I'm saying, that's fine. Don't worry about it. Just know that it's another way to compute correlation. And it does this by comparing every single pair of observations possible to each other. All right, now, it was kind of complicated what I said a moment ago, right? And I mean, honestly, it is. And if you think about what I was saying, it's kind of a slow computation to go through. It's a slow check, and because of that, this is the slowest of the 3 correlations to compute. This is really the best time to use this is when you have data with a lot of repeated values. So let's say I have one vector that has all 1s and 2s, and another vector that has all 0s and 1s. Honestly, Pearson and Spearman correlation probably aren't going to do the best job of detecting relationships in here. If I have like the limited, like distinct values in the data set, usually that's when Kendall's tau, the concordance correlation, is best to use. So this is best to use when I have a lot of repeated values in my data set. All right, so now let's go ahead and get our data. So once again, I'm going to the same URL base, and I've got a different in file. Let's take a look at it. What do we get? Here's my X, here's my Y. Now let's go ahead and compute the correlations. So here, I'm going to store the correlations in something called core. And we're going to use stats to get the Pearson correlation. Then we're going to use stats to get the Spearman correlation. And then we're going to use stats to get the Kendall's tau correlation. All right, so now let's take a look. Okay, so we can see that Pearson gives us like a 0.792 correlation. Spearman will give us 0.754, and Kendall will give us 0.576. Okay, so something about this. In general, not 100% of the time, but in general, Spearman correlation will give us a larger correlation in magnitude than Pearson, but it's not 100%. This is one of those times that it didn't work out that way. Okay, so this tells me that since Pearson comes out larger, I'm more confident that a straight line relationship is the way to go. And the big drop in Kendall's correlation tells me that there's probably some like repeated values in there. All right, a moment ago, I said that when you do Spearman's correlation, you're taking the rank statistics and you're running Pearson on that. So let's go ahead and let's compute that. And let's double check to make sure that I'm telling you the truth. All right, so we're going to take the rank of our data on X. We're going to take the rank of our data on Y, and then we're going to compute the Pearson correlation. All right, so now we're going to go ahead and print it. All right, so if I use Spearman's correlation, we get 0.754. If we use Pearson's, we get 0.754. All right, so we get the same value. That gives us confidence that Spearman's correlation is, in fact, just rank correlation. All right, so just to reiterate some things, when I have Pearson correlation, that is straight line correlation. So I'm assuming there's a straight line relationship. It's not something more exotic, more interesting. That's y equals mx plus b. Pearson is the fastest one to compute. Spearman correlation is rank correlation, and it's better for detecting non-straight line relationships in data. The Kendall correlation, that checks pairs of observations. This is the slowest to compute, and this is best to use when we have like very few distinct values. We have a lot of repeated values in our data. All right, this is all I've got. I hope you're doing well, and take care.